I think we were here, theorem 102, last time. We were on irreflexivity for order, so let's jump right in. So for any given natural number n, it is not the case that n is less than n. When a relation has the property that things do it with themselves, then you say the relation is reflexive. So like axiom 1 tells us that equality is reflexive, right? So this is like the opposite. This is saying that for the less than relation, it's not. Not only is it not reflexive, but things actually do not have the reflexivity relation with themselves. They do not relate to themselves. So this is also kind of interesting if you think about less than. The way we defined it is membership, right? So this is proving that natural numbers are not elements of themselves. And it's actually going to take effort to prove. It's not automatic. So although it's difficult to create or find an actual situation where you have something, some set being an element of itself, it's still, with just the axioms that we have put down, we don't really have a way of proving that things are just not in themselves. Maybe it is possible to have some sort of circular containment thing. We just haven't said one way or the other anything about it. Some people will introduce axioms that specifically like disallow this completely. So we haven't fully disallowed it, but we're going to show that the natural numbers are a specific context where it just doesn't happen. So this will be done by induction, and you're probably getting used to this by now, so I'm not going to assume n is a natural number for my first step. I'm not going to fix n because I'm going to do induction on n. So we will prove, and then I'm going to say exactly what it is that I'm going to use induction to prove. So it's always something like this, right? I'll prove that for all natural numbers n, and then something about n. And here the something is this. So what's playing the role of my capital phi in my application of the mathematical induction theorem? It's this, right? With the x's getting replaced by different things in here as I look at the different parts of the theorem that I'm applying. Okay, so there's a base case, and there's an induction step. And for the base case, we must prove that it's not the case that 0 is less than 0. Okay, but hang on. So 0 is just another name for the empty set, right? So since 0 is just another name for the empty set, this is just true by theorem, was it 11? No, that was the definition. Theorem 12. It's just true by theorem 12. It's for any given thing, it's not going to be in the empty set. All right, induction step, assume n is a natural number, and so suppose n is a natural number, and suppose that it is true. The thing we're trying to prove is true at the level of n, and then we're going to try to prove that it's true at the level of next n. So here, at this stage, our goal becomes to prove that it's not the case that next n is less than next n. So how do we prove that something is not the case? Well, usually, unless you have a pretty good plan in mind, which I don't at this point, unless you actually have a pretty good plan in mind, proof by contradiction is a good approach because it gives you something to work with. So let's suppose, for the sake of contradiction, that in fact next to n is less than next n. See now, so we're supposing that the thing that we're trying to disprove is actually true. Now, if we get a contradiction, then we will have proven the induction step, and that'll be it. So goal now is just to reach a contradiction somehow. So you see how proof by contradiction gives you something to work with? So now I sort of have more to play with. So if I just play around randomly with things, then I have more of a chance of possibly finding something useful than before. Okay, so what do I have to play with? Next n is less than next n, and it's not the case that n is less than n. Somehow from those things I want to reach a contradiction. Well, I'm seeing this less than next combination there. So how about I mush those together, as I seem to be doing a lot in this section. So then next n is less than or equal to n. That's theorem 96.2 for the bajillionth time. So that, let's see. I mean, it gives us cases at least. It tells us that next n is either equal to n or less than n. And yeah, so let's see where we can go with the cases. So case 1, suppose next n equals n, and then case 2, suppose it's less than. And now my goal is to get a contradiction in each case. And what I'm going to contradict somehow is probably the fact that it's not the case that n is less than n. Well, if next n equals n, and I know next n is less than next n, then by axiom 2, theorem 4, whatever, by that principle that you can replace things by things they're equal to, and retain the truth of a proposition, I can replace next n's here by n's, and then I get n less than n. So then by this, n is less than n, right? But that contradicts that I literally said that that's not true just now. So contradiction. All right, so that's it for case 1. Now if I get a contradiction in case 2, then the proof by contradiction is done, and the induction step is done, and the theorem is proven. So let's suppose next n is less than n. So what seems to be contradictory about that? It definitely feels contradictory, right? I mean, if this dot here is n, this dot is 0, and there's a bunch of stuff leading up to 0, then I always imagine that next n comes after, right? That's the idea of next, it's the thing that comes immediately after. It's the successor. And yet here we're saying, suppose next n comes before, so suppose next n is off that way somewhere. Could that be? Could next n be the immediate successor of n, and also be somewhere in between 0 and n, somewhere less than n? It really feels like a contradiction, but what's the actual contradiction? What's the exact contradiction? So it feels like a contradiction, but to really get a contradiction, I need to prove that some particular proposition is both true and false. That's what a contradiction is. So how do I get this idea? How do I turn this idea into an argument? So here's the two things that seem to be in conflict. One is that next n comes immediately after n, right? Okay, where's the formal, rigorous justification for that picture, that next n comes immediately after n? It's actually right here, very early on, just straight from the definitions of things, our essence theorem. Things are less than their next. So that at least tells me that next n comes after n. And then this is telling me next n comes before n. Now that feels contradictory, but why would that be contradictory? Why can't something both come after and before something? Well, that seems to violate, if something comes both after n and before n, it almost feels like we've lined things up in a circle, like we've wrapped around. We're violating the linear ordering of our counting numbers. Here's specifically what ends up getting violated is transitivity. So transitivity is telling us that, when you have one thing and something after it, and then something after that, then the ordering is sort of preserved from beginning to end. So this is an important component of the picture of things lined up next to each other like this. So with these two hints in mind, and with the knowledge that we have already proven Theorem 100, we're currently working on Theorem 102, so Theorem 100 is available, we notice that, hang on, next n is less than n. Well, since everything is less than its next, and since we have transitivity, look at this, next n less than n, which is less than next n, so we have, look at it in this order, n less than next n, which is less than n. So let me write it like this, n is less than next n, which is less than n. So n is less than n by Theorem 100, by transitivity. Okay, that contradicts the induction hypothesis, which is literally that it is not the case that n is less than n. So contradiction. Yay. All right, so natural numbers are not less than themselves, which interestingly also is saying natural numbers are not elements of themselves. Okay, before I stop looking at this theorem, I want to show you something very cool, a small thing that we can now immediately prove, that where I think the proof is really interesting and kind of funny. So the set of natural numbers is also not an element of itself. So how would we prove something like that? So if you want, you can pause the video and see if you can come up with how to do it. There's a way to do it using this theorem. But either way, here it comes. So try proof by contradiction. Suppose the set of natural numbers is itself a natural number. Then what does Theorem 102 say? Theorem 102 says natural numbers are not elements of themselves. So by Theorem 102, if the set of natural numbers is a natural number, then it must not be by Theorem 102, it must not be less than itself. That's what Theorem 102 says. Right? Natural numbers are not less than themselves. So in other words, since less than is just a fancy way of writing membership, it's not the case that, you can write it like this, it's not the case that the natural numbers are in themselves. But then this is a contradiction. I assumed n is an n, so then n is not an n. Contradiction. And that's it. That proves that in fact n is not an n. So that's, I really like that. The overall structure is if n were an n, then n wouldn't be an n, which is a contradiction. So therefore n isn't an n in the first place. Now this probably looks a little bit ridiculous, the question of whether the set of natural numbers is a natural number. Of course the set of all natural numbers is not a natural number, right? But actually it's not that weird. The set of natural numbers does have a lot of similarity to, does have a lot of similar features to those features that actual natural numbers have. So for example, if you have, so let's look at the first few natural numbers. You've got the empty set, then you've got a set containing the empty set, and each natural number sort of just is a set that contains the previous ones, right? And what we just proved is they never contain themselves. Now, can you imagine what would happen if you kept doing this infinitely? You would eventually build the list of all natural numbers, right? So in some sense, if you continue counting forever, actually forever, then, yeah, so let me put it this way. If you count up to 2, 0, 1, 2, then you have built 3. If you count up to 4, 0, 1, 2, 3, 4, then collect what you've counted into a set, then you have built 5. If you count up to 9 and then collect the numbers that you've said into a set, then you have built 10. If you count forever and then collect everything together that you've counted, then you would build the set of natural numbers. So it's kind of an infinity, right? The set of natural numbers is kind of like an infinite number. It's kind of interesting. So this is sort of like saying that infinity is not one of the actual numbers. And people actually do set up systems of counting where they will include this. And they'll say, well, this is like our first infinite number. And then they allow themselves to keep counting from there. So you know how we get from one number to the next? We just use the next operation, succession, right? So 0 to 1 just involved building a set that includes the previous stuff, but also 0 itself. 1 to 2, build a set that has the previous stuff, but also 1 itself, and so on. So you can keep doing that, actually, even when you reach infinity. You can do next n, and then the next of that, and the next of that, and so on, and build larger things, like what you might think of as infinity plus 1, infinity plus 2, and so on. When you do this, and oh man, does it keep going, you create what are called ordinal numbers. We build all of these. It's really fun stuff. All right, but that's a sidetrack, so let's get back to the main stuff here. Let's move on to Theorem 103 in the next video.